So now I want to talk to you about something a little different, okay? You now have a good idea what discrete math is. The next obvious question is, why are we studying discrete math? And to answer that, I first want to tell you something that's a little strange, and that is that there's actually an organization called ABET, and they certify engineering programs, and they certify computer science programs. And they have certain requirements that programs need to meet in order to be certified as a real computer science program. There's only one course that they mention specifically by name and which simply all programs must offer. And yes, that is discrete math. So the accreditation body actually thinks that discrete math is fundamental in computer science. I'll tell you even more. Some people believe that classes in math like calculus actually shouldn't be required of computer science students. Perhaps instead computer science students should take more discrete math courses, 2 or maybe even 3 courses in discrete math. So this is really a fundamental topic. Now the question is why? Okay, and I've got a couple of answers for you. The first answer is simply this. We talked about discrete math as being the math about things that come in discrete chunks, right? And it turns out that that is exactly the kind of math that we're talking about for computer science objects. So discrete math describes cosi objects, okay? For example, let's say that you want to think about a class. And I'm talking a class here as in a Java class, okay? Then it's got some methods, okay? Each method has a behavior that tells how it maps inputs into outputs, okay? And you might also change the inputs and use those to modify the state of the object. Okay, so that's something that you might see in a typical program, right? Well, these are actually discrete things, right? Inputs to outputs, that's a conversion that takes place, kind of like one of those functions that we talked about earlier. And modifying state, that means that the state was something like this, S0, right? And then I modified it and it becomes S1. Then I modified it and it becomes S2, and so on. You see discrete changes, right? And for instance, when I change the number 3 to the number 5, it goes straight from 3 to 5. It doesn't do something strange like it becomes pi in between, as if you were turning a dial. That would be a continuous action, right? More than that, if you look at each state here, what exactly does that mean? And that is the value of some variables, right? So the class will have some internal variables, and the value of those is what we mean by the state of an instance of that class. What can those values be? Well, each one of those values, and let's just talk about basic types, okay? But each one of those values might be, for example, an integer. That's discrete, okay? And it's even worse than that. It's there might be only 32 bits, so I can't have all integers. I only get so many. The same goes if it's a floating point number, okay? And that's because I only have 32 bits to store it. Then there's only so many different numbers that I can store. That is a discrete quantity of numbers. If it's a double, okay, then I may have more. I may have 64 bits, but that's still a finite number. It's still a discrete sequence of numbers that I can have. There are actually circumstances where I have a number in floating point, and it's reasonable to ask, what is the next number that I can represent? Which of course would be ridiculous to ask about the real numbers, right? So all of the objects that we have in computing are actually discrete objects, right? That's why discrete math is so important. And in fact, I don't really exaggerate when I say that computer science is in many ways a applied discrete math. That's what we study, okay? So that's one reason that we do this, okay? Now, there's actually another reason, okay? And the other reason is that we get abstraction, okay? And what do I mean by that? What I mean is that there's a lot of problems that look different, but if you can abstract from really far away, they actually end up looking exactly the same. And abstraction is what we do as computer scientists to be able to solve problems. So we might recognize that that is actually exactly like that, which I've already seen. So here are some of the benefits of abstraction. You can think of many different kinds of problems. Like here's an interesting problem you might solve. How many semesters is the absolute minimum to graduate with a computer science degree? Okay. And that's actually a hard problem to solve, but you can kind of try to figure it out. Here's another problem, which is seemingly very different. Suppose that you have a chain of command, like you have a general, and the general has some colonels, and the colonels have majors, and all the way down. And somebody on the field has to make a decision. Okay, each decision has to be verified by their officer, their immediately reporting officer. So how long does, say, a tank commander have to wait before they can actually fire upon the enemy? Because they've been waiting for a decision all those levels up. It happens that both of those questions are actually the same. Right? They're both graph problems, and once you understand that they're graph problems, then you can solve them in the same way, which means we already know how to do it. Okay, so that's what abstraction is. We're going to eliminate all the details that don't matter, and actually that way be able to recognize things that are really similar, even though they don't look the same. Okay. We're going to see problems like this in this class. You're definitely going to see problems like this in your next class. If you're in the computer science sequence, which would be algorithms, okay?